Okay, so time to get started. Apologies for the weird arrangement with the cord there. So apparently something must be wrong with the built-in, touch screen setup, and it looks like this is probably somebody's solution to just plug straight into the projector. So I guess that'll be fine for today, and I'll let someone know, and hopefully they'll be able to fix it by next time. Okay, so here's where we were. We were talking about flux. And recall that we talked about flux long ago, and all the stuff that I have here is old news. We've already discussed all of this stuff. In particular, this is the formula for flux. These are the interpretations. But all of this was under the assumption that the vector field was constant and that the surface was flat. So what we talked about last time was how to sort of adapt that to if you have a curved surface and a non-constant vector field. And hopefully no surprise, we chop the surface up into little pieces like so, right? Each one is approximately flat, the vector field is approximately constant, and life is good. You just work it out on each piece and then you add it all up. The one complication we had to throw in is that we did have to refine our idea of a surface to include this idea of an orientation. We need to know which direction is the one that we're going to consider the positive direction through the surface. Kind of analogous to when we talked about orientations of curves, we needed to be able to say which direction is the positive direction along the curve. Now, notice along the curve, but through the surface, right? So they're geometrically different, but they're conceptually pretty analogous. Okay. All right. So our punchline was we wrote down all of this right here, and this is just a kind of, again, the whole is the sum of the parts argument. On each little piece, we had an easy formula for flux, and then we add up over all the pieces. And then we ended by talking about this notation right here for the ds vector as being that times that. And again, reminder, that just is kind of a notational ripoff from vector line integrals, where we did something highly analogous. Okay, all right, and that's where we left off. So how are we going to compute these things? And the good news is we already have everything we need, pretty much. We just have to put the pieces together. So, reminder, we just got through talking about all this stuff. Nothing new in the green. That's recopy from the previous page. And all of this stuff is a recopy from several pages back. We've already talked about how you can view a surface as being the image of, well, in fact, a parameterization. Right? We've talked about how to parameterize surfaces. We've talked about how to compare that area to that area. Therefore, we've talked about this stretching factor being the magnitude of capital N. All that's old news. So all I'm going to do here is take, let's see here, this formula, and stick that in there. Right? And then I'm going to come down here and I'm going to look at these two things, that and that. Now let's look at what I have in purple here. Capital N is a vector. It has a direction and a magnitude. The direction of capital N being a normal vector, wouldn't you think the direction is the unit normal vector? That's the unit normal vector perpendicular to the surface. That's the direction that this non-unit vector perpendicular to the surface is pointing. So you'd figure. And of course, the magnitude of capital N is quite literally the magnitude of capital N. So this seems to be just a rewrite. That little n times the magnitude of capital N looks like a duck, quacks like a duck, feels like it ought to be a duck. Right? Okay. Now, you will notice what I have written here on the page. I've put an asterisk here. I put this in here because I have actually just said something that's not true. I've committed a little math crime. I did it on purpose. I'm doing it for dramatic purposes. right? Also, because there's a subtlety at play that I don't want to be distracted with right now. I want to get to a formula. I want to get a win in the win column. I want to get an example computed to our satisfaction so you can see how the mechanics of this tends to work. But we're going to have to come back and talk about this because technically what I've written here, not really quite true. Okay, so if you want to try to anticipate what did I do wrong here, feel free to think about that. Okay, so taking this formula, we now have a parameterized formula for how to compute flux. You want to compute flux? Okay, plug and chug right here. Okay, so let's do one. This is a quickie. Again, it says compute the flux, so we recopy that formula we just wrote down. But let's see now. We've got a vector field. We've got a surface. We know that our first step is to parameterize. Okay, fine. I guess we have to parameterize. How are we going to parameterize this right here? Z equals x squared plus y squared. Well, it's a graph. And we do have various tools in our toolbox for parameterizing things. But when you're looking at a graph, you want to think very strongly about using the graph parameterization. So that's what I'm going to do here. This being a graph, the graph parameterization is that right there. And that's going to be our best choice for this exercise. Let's see here. We take the appropriate partials, as is our formula. We take the cross product, as is our formula for capital N. And there you go. There is our capital N, exactly as we just computed. Now, the one other little thing, you do have to rewrite your vector field. Now, our vector field is given right there, so you've got to write z squared, x squared, y squared. Now, that does not appear to be what I have here. So, why did z squared, x squared, y squared turn into this? Well, you got to keep in mind we're pulling back through the parameterization, and this z right there, in the formula we're given for our vector field, that z from the parameterization is s squared plus t squared. And so that is what goes in place of z. That makes sense to everybody? It's plugging in the formula for z given in the parameterization. Okay. All right, likewise for x and y. X, well, x, it says right there, is s, and thus that s right there. Okay. Okay, so how are we doing on this example? Is everybody feeling pretty good? Very plug and chug. Okay, so what did I do wrong? How did I cheat, right? What's wrong with what we just did here? And it comes up as a result of orientations. And I deliberately, again for dramatic purposes, I deliberately swept some subtleties under the rug. In fact, there are two separate, not to be assumed to be equal, unit normal vectors at play here. So let me remind you what they are. So we talked about when you have a surface. We kind of reminded ourselves of this at the start of today. We're going to have to indicate by way of a unit normal vector, we're going to have to indicate what we mean by the orientation of our surface. Now, it could be in either direction. The surface could be oriented in either direction. And whichever one of these you choose, that's what we're going to call the orientation unit normal. That is the term that we've already indicated for that unit vector. Now, here's the thing. When you parameterize your surface, think back to all the parameterizing that we did several days ago, whenever that was, right? And we had various different parameterization methods. Notice we didn't talk about orientation at all, right? When you parameterize a surface, you're just not thinking about, are you inadvertently, accidentally also creating an orientation? But in fact you are, because as follows. When you write down your parameterization, that determines your partial derivative vectors, whose cross product determines your capital N vector, the direction of which gives you your what we call your parametrized unit normal. All right, so the parametrized unit normal comes out of your parameterization, thus the name. The orientation unit normal comes from the statement of the question, or whatever it is that's intrinsic to the surface that's been given to you. That's not up to you, right? Whoever's asked you the question gets to decide, which way that goes. Okay, so these two vectors may or may not be the same. The parameterization was done independently of any consideration of the given orientation of the surface. So it's a coin flip. You might, when you parameterize, you might have picked the right normal vector. Maybe, but you just as likely might have picked wrong. Okay, so that was my crime. That's what I did wrong here. When we started off here and we were talking about flux, and we talked about, little n, that little n when we first write down flux is based on how the question comes to us. Whatever the surface, whatever our oriented surface was given as, this is the orientation unit normal. But then when I made a comparison to the capital N vector, right, the capital N vector, of course, yes, it does have a unit vector direction and a magnitude that make it that are those two sort of two sort of elements. The direction is the parametrized unit normal. These may or may not be the same. Again, coin flip. Right? So when I claimed that, let's see here, color choices. When I claimed that this was the same as that, not necessarily, because the green orientation unit normal might not be the same as the purple parameterized unit normal. That's the problem. That was my math crime. Okay. All right. So bad news, good news. The bad news is it's really hard to see this coming in advance. It's really hard to tell as you write down a parameterization which way are you orienting it. It's very hard to look and glance and see. Here's the good news. Don't worry about it. If you pick wrong, you can just fix it by multiplying by -1. It's as simple as that. Right? So I'm going to show you an example where this is in action, but I just want to get it written down for the record here that our ds vector, we've stated it before that the ds vector is capital N du dv. We've some equivalent version of this, and what we have to now be careful about going forward is that this does not account for possible orientation issues. Keep in mind the ds vector points in the direction of the orientation unit normal. ds is intrinsic to the surface. It's never heard of your parameterization. It does not care about your parameterization. Whereas capital N comes straight out of the parameterization and has never heard of your, what was the orientation given to your surface. You parameterize completely independently of that. So they may or may not be in the same direction, and so there's an unknown plus or minus right there. Okay, let's do an example. Let's see how this works in practice. What I expect from y'all on exams and homeworks and stuff. So, yeah. Here you go. Example question. By the way, it hopefully looks familiar. This is the example we just got through looking at just a couple minutes ago. Same vector field. Same paraboloid. Again, looking at the portion above the same unit square. Everything's the same, except I'm now going to take this as being oriented downward. All right, so we're going to compute. This might be phrased as we want to compute the downward flux, or you might say the flux through the downward oriented paraboloid, or various different phrases. Okay, so there's my given orientation. What do I do with that orientation right off the bat? Nothing. Don't worry about it. Ignore it for the moment. We're going to go ahead and parameterize however might be most conveniently. Right? I think the graph parameterization is hard to beat in a case like this, so we'll use the graph parameterization. We'll compute those derivatives. Yeah, fine. We'll take that cross product, as per usual, to get our capital N vector. No problem. Don't worry about it up to this point. But here's where you have to pay attention. Now, I know which way my surface is supposed to be oriented, and now by looking at my capital N vector, I can see which direction I have inadvertently oriented it. And you can see from this this plus 1 right here, right? You can see that plus 1. I can't justify calling that downward. Right? If anything, this is somewhat upward. It's definitely not in any sense downward. And so apparently I have guessed wrong, and I have to mea culpa on that. So yeah, I parameterized backwards. Am I going to redo the whole process? Am I going to come up with a brand new parameterization, hoping that my brand new parameterization will be oriented the right way? No, don't bother with that. Just fix it. I messed up my orientation. I fix it with a minus sign, and I proceed. And everything's all better. That make sense to everybody? All right. The toughest thing about this, frankly, is remembering to do it, right? It's very, very tempting to, you start off with your parameterization, and, you've taken that deep breath, and you're plowing forward with your computations, and it's very easy to kind of just, and just kind of go with what you wrote and just not even think about it. And that is, unfortunately, a really big deal. There's a temptation to say, well, it's just a sign issue. It's just a minus sign. Sign errors, what's the big deal? Well, again, it's not about answers. It's about ideas. And where this minus sign comes from is involved with a sophisticated, significant idea from the material here, namely, what is an orientation of a surface, and how might my parameterization actually be incompatible, and of course how to fix it, right? So anyway, big ideas afoot. The punchline of the big ideas is just a minus sign, but it's still big ideas. So I want you all to be prepared. On an exam, if this were a 20-point question to compute this flux, I wouldn't be surprised if the orientation were something like 4 or 5 points, something like that. It's a big deal. It's one of the big ideas. So make sure to always pause at this point right here and think, did I orient it the right way or the wrong way? Yeah?
Does the flux direction have to be given like that?
Yeah, well, that's right. So if I hadn't put this in here, right, if I had just not said anything, and if the question had just been compute the flux through, this surface, then the question's ambiguous. And that would be a poorly written question. And now I will confess that, sometimes for the same reason that students might not think about that, sometimes the question writer might not have thought to think about that. It's possible that if that happens on an exam, then just please come up and let me know, and I'll clarify, and that's totally my fault. Yeah. I think I'm beyond that level of oops at this point, but we'll see. Yeah. Okay. Now, there's one other thing I need to emphasize about that, and that is where you put the minus sign. This also matters. Again, it's about ideas, not answers, so we've got to be careful with that. I want to go through this calculation here. Of course, we haven't made it all the way through yet, but I want to go through and document where does the minus sign need to be. Okay, well, we were asked about flux. The question itself comes with an orientation given. Of course, when I write down effectively what the question is asking, that is a representative of the given orientation. DS, likewise, is a reference to the given orientation. DS is intrinsic to the surface. So that is what I've been coloring in green. But this integral right here, you see, the orientation is going to be wrapped up inside of this capital N. Capital N comes from the parameterization. This is not intrinsic to the surface. This, what I have in purple here, comes from the parameterization. So that's where the switch happens. All the integrals that follow come straight out. Oh, I missed again. All that follows comes out of the parameterization. So the minus sign needs to go there, and likewise there, and likewise, of course, it follows along throughout the calculation. Does that make sense to everybody? Okay. The reason you have to be careful about this, and I know y'all been doing math for a long time, and a lot of the classes you've had in the past, especially high school and probably prior. All that matters is the answer in a box down at the bottom of the page, and I cannot emphasize enough that's not representative of how math is really done. You have to think about what you're writing in advance. In addition. So let me just point out what would be wrong if you placed the minus sign at the wrong stage. If you were to, let's see here, let me do this. If you were to not put that minus sign right there, hypothetically, right? And if you were to put the minus sign there for the first time. Now let's think about what is written on the page. What is written on the page is wrong in two ways. What is written on the page, first of all, it would seem to suggest you've written right here that green integral is equal to that purple integral, and no, they are not. They are opposite. That's the whole point of this conversation, is that those are negatives of each other, and yet we have it written on the page that they're equal to each other. That's not true, right? And truth matters. This is math. That's, that's how that works. Likewise, this equation also not true. This, as is currently written, having left off that minus sign right there, suggests that these two integrals are negatives of each other. They're not negatives. These two purple integrals are equal. They're not negatives of each other. So that's wrong too. Right? Now, anyway, from the point of view of only the answer matters, this is all silly fussiness. Right? But from the point of view of we're looking at your reasoning. We want to measure from your reasoning how much do you really understand the ideas afoot, right? Getting this wrong suggests that you might not be entirely clear on whether these are the same or different, and it brings your understanding into question. So please do be careful about this. It is important, and I'm not going to make any comments as to how that would be graded, but it would be something that graders would think about, as they should. Okay, so let's talk about language a little bit. There is something intrinsically awkward about talking about this kind of thing. Let's suppose we're thinking about this surface right here, for example, paraboloid, kind of like the one we were just talking about, and I described the orientation as being downward. Right? Well, what do I mean by downward? Well, I was talking about this orientation like that, where the normal vectors are all kind of, sort of downward-ish. On the other hand, there's also another option. The surface could have been oriented upward. And I think upward versus downward is fantastic language for distinguishing between these two orientations. Now, the point here, the problem, what a lot of people will be uncomfortable with about this language to describe these orientations is that these green vectors are not all pointing straight up. They are mostly not pointing directly upward. So if I say upward, that's sloppy. Right? It's just not exactly right. But you got to keep in mind, this language, the job that this language is trying to address is merely to distinguish between two possibilities. We're not going to compute
on the basis of that language, right? We're not going to look at upward and think, oh, that must be 001, right? That's not what we're doing with it. We're only trying to distinguish between these two possibilities. And with the idea of just distinguishing in mind, this is completely clear. No one would ever look at the word upward. Oh, man. Okay.
Sorry. There it goes. The little cable, the way it connects to the laptop, has got a lot of play in it. So sorry, it's going to be a little touchy sometimes. No one's going to look at this word upward and think this blue orientation. None of these blue vectors are in any sense upward. They're all at least somewhat downward. Right? And vice versa. The word downward, no one would think this green orientation. It's not perfectly descriptive, but it removes all possible doubt. It removes all possible ambiguity. So that's the job of the language. The language's job is not to be precise. The language's job is to remove ambiguity. Now, that in mind, inward versus outward. A lot of students kind of like this idea, inward versus outward. The slight problem with this is technically this is not a closed surface. There is no inside. Technically, right? So inward versus outward, a little bit awkward. Nevertheless, most people would probably know what you probably meant, but it's still, I think that's suboptimal at best. Okay. Now, different surface, different language issues. So, for example, let's think about a sphere. And a sphere has two possible orientations. There's that one, and there's this one. Right? So how would you distinguish between these? Now, we were very happy with the paraboloid with this language, upward versus downward. So I don't know, maybe let's think upward versus downward. Does that do the job? No, it really doesn't. Upward? Some of these green vectors are upward. Some of the blue vectors are upward. Upward does not remove the ambiguity. I don't know what you mean. If you say upward, I don't know whether you're talking about green or blue. Likewise, downward. But in this case, there really is a closed surface here. There is an inside and an outside. Inward, unambiguous. And outward, also unambiguous. So the right language to use depends on which surface you're talking about. And you've just got to think about your surface, think about the two possible orientations, and think about what aspects of those vectors will distinguish the one group from the other, and choose your language accordingly. So I hope that all makes sense. Does anyone have any questions about all this language business? Okay. All right. Okay, moving along. Sometimes you get lucky. Kind of like with vector line integrals. Remember, we talked about a couple of different ways in which you can get really nice geometric fortune just kind of lands in your lap. Here's an example of that in this case. You look at this example right here, and if you were to brute force this, well, okay, we're going to parameterize the sphere. Lots of trig shows up, and we're already pretty unhappy just because of all the trig. Right, so I don't really want to have to brute force this. But check this out. Spheres have tremendous symmetries. As we've observed in other contexts, the position vector for a point on a sphere, namely a sphere centered at the origin, the position vector and the normal vector are parallel. That's a peculiarity, a lovely peculiarity of spheres centered at the origin. Only spheres centered at the origin, right? So because these two vectors point in the same direction, they're multiples of each other. I know this one has magnitude 3, so magnitude 1 I would get by just dividing by 3. So I get a really convenient, I didn't have to parameterize, take derivatives, do a cross product, divide by the magnitude. That whole tedious That would be so tedious in this case. I didn't have to do any of that. And I can just immediately write down that formula for my normal vector. And combining that with my vector field that was given, I can just crank out the dot product. This dot product, pretty clearly 0. My answer is 0. We walk away, right? Didn't have to get any dirt under our fingernails. It just falls in our lap.
Just
Yeah.
one question.
Yeah, sure.
I'm just still a little confused about where did the vector x come from?
Oh yeah, so the vector, that's just my notation for x comma y comma z. That's the position vector for this point. So that point has coordinates x, y, z, and position vector just means the vector which has its tail at the origin and head at that point, and it's, yeah, right.
Okay.
Is that satisfying?
Yeah.
Okay. Everybody else? All right, so neat trick. Look for geometric good fortune like that. Here's another example. Different geometric convenience here. Here we have a pretty weird looking surface. Kind of scared of this inequality here. It's chordic. I don't like that. Right? I could parameterize it. By the way, graph parameterization, something to think about, right? Y is a function of x and z. In fact, it's a really convenient function of x and z. So this is easy to parameterize. So you could brute force this, but you're going to end up with some weird bounds because of the x's and z, that inequality with x's and z's. So here's the much easier way to think about this. We're looking at this plane. Our surface is part of that plane. Being as our surface is part of that plane, every point in our surface has the feature that y is 3. So, if y is 3 at every point on our surface, then this is 0. Right? The ugliness of this second coordinate, it's always 0 for every point that we care about, every point on our surface itself. So the vector field simplifies really nicely. As a result, our vector field, second coordinate, I'm just going to call it 0. Everybody see what happened there? It's real cool. Now, there's another nice thing that happens, independent of the plane having y equals 3, is the fact that y is a constant. And when y is a constant, my normal vector is easy to write down. This being y equals a constant, this plane is perpendicular to the y-axis, which means the normal vector is parallel to the y-axis. So again, easy to write down what little n is. And little n, 0, 1, 0. Now again, I haven't really done any work yet, right? I haven't done any plug and chug to speak of, and yet, again, we already win. This dot product is already clearly 0, and so my answer is 0, and we celebrate and walk away. Everybody happy? So heads up, life is good sometimes. Capitalize when you can. All right. Okay, we saw some time ago, I don't know, it might have been last time, I lose track of the days, but fairly recently we talked about coordinate line integrals. And the idea of coordinate line integrals is a sort of a notational alternative for a vector line integral. And it's kind of clunky, but it just comes from taking our formulas and cranking them out in coordinates and just writing them down, and that's what comes out. So that's all I'm going to do here. Old formula for the ds vector, old formula for capital N, and let's write it out. Oh, whoops. Here we go. Let's write that out in coordinates. Well, there's xs in coordinates. There's xt in coordinates. Here... colors are hard to hit. That cross product. There's that cross product in coordinates. You may recall I made a vague reference a few days back to these Jacobian determinants, these two-dimensional change of variable stretching factors being the coordinates, oddly, of capital N. It's really sort of weird how that turned out. But anyway, here we are again. There are those stretching factors. So having written that down, now we look at what we have, our ds, right? That, distribute the ds and the dt. And now let's just look at those coordinates, one coordinate at a time. And I think it's a pretty easy pitch that we ought to call that dy dz. Right? Now, again, little math crime. It's as if the ds and the dt cancel. And they don't, but it's as if they do, just like we saw back in change of variables. And then likewise, it's a reasonable choice to call this dz dx and to call this dx dy. So with those notations chosen, we now have a new option for how to write down a vector surface integral, our new toy that we've been playing with since last time. And in particular, ds is that, and f has coordinates 2, so it's that. And then you write down the dot product. So this great big dot product is this. And we're done. We have ourselves a new notational alternative for a vector surface integral. So in lieu of writing integral f dot ds, if you want, you could instead write integral p dy dz plus q dz dx plus r dx dy. Now, do you want? Would you want to do that? I don't think in most cases most people would. Right? What's to be gained? Looking at this trade-off, looking at our options here, which one of these is easier to write down?
Well, I think you've got to go with this vector notation. It's much more compact, right?
Which one is more intuitively, like which one do I have a physical interpretation or geometric interpretation of the objects?
Again, with the vector notation, the vector field F comes from the physics of the scenario, maybe fluid flows, for example. That means something. ds talks about a little piece of surface area. That, again, means something natural.
All this business here is relatively sort of like not clear what it is or why we're writing it down. So I think most cases, certainly in Math219, you're going to want to go with that notation right there. So just like with coordinate line integrals, why am I showing you this notation if we're never going to want to use it? And two reasons. One, cultural. There are powerful ideas afoot here. It turns out that this is kind of what differential forms looks like. And that's the super powerful tool that if you really want to crush all of the stuff that we're talking about here in sophisticated ways, you do it with differential forms. That's well beyond what I think is reasonable for this course, so we're not going to do it at all. But there are great reasons to want to use this notation when you're doing those more sophisticated things, which we are not. So, again, why do you need to know? Well, because other people like this notation. They like this notation, I would imagine, because of these reasons right here, right? Because of other powerful things that you can do with them. But again, I don't think you're going to see those. What I think you're going to see is you're going to see this notation used for no particularly good reason, right? And when you see this, I just need you to know what to do with it, right? If you get into some future engineering class and you see integrals written down like this, you just need to know what they're talking about. And the thing to remember is they're just talking about a vector surface integral. So in particular, this business with the dy, dz, dz, dx, etc., that's just a fancy way of saying the ds vector. That's all it is. And likewise, what's the p and the q and the r? That's just a fancy way of telling you your vector field that's relevant to the integral in question. So that's all that's going on there. Pausing for questions. You willing to buy all this? Okay. All right. All right, moving along. Symmetry theorems. By the way, real quick, before I go on, symmetry theorems. We talked about symmetry theorems for line integrals. The coordinate versions of integrals. We talked about that for line integrals. Geometric good fortune. We talked about that for line integrals. I hope you're noticing that the ideas that we can use for surface integrals, even though they're totally different physical motivations, totally different geometric kind of contexts, there's a lot of analogies between line integrals and surface integrals. And we're going to hit that point again in just a minute. Okay, so let's go into the details of symmetry theorems. You'll recognize, if only by the layout on the page, this theorem. It's a brand new theorem, but it's totally analogous to several previous versions. We've seen a symmetry theorem for single variable integrals, double integrals, triple integrals, scalar line integrals, and now same theorem, again laid out on the page, same for that reason, now for scalar surface integrals. And it's exactly the theorem you think. If you have a scalar surface integral, and if your integrand is odd, and if your domain is symmetric, that is both, mind you, over the same plane, very importantly, then your integral is 0. And you check those conditions, declare victory. Yeah? Believable? I think it's pretty believable, right? It's exactly what you would sort of expect. Okay. All right. You'll remember when we were talking about scalar line integrals, we made this same emphasis that it's only for scalar line integrals. And you see here we're making the same emphasis here. This is only for scalar surface integrals. Why can't we do it for vector surface integrals? And the punchline, short version, if you have a nice symmetric surface, as I attempted to draw there, right, symmetric through a plane like that, for example, notice the vector surface integral, like so, which you could rewrite like that, has a normal vector involved. And these normal vectors are just not the same. Yeah, that's all it is. This little piece of area can have the same scalar area as that little piece of area. No problem. But the normal vectors are not the same. They're also not negatives of each other. They're just different. Right? So we're kind of, I'm going to say we're dead in the water. And certainly it follows there is just no odd symmetry theorem. Odd symmetry will not work for vector surface integrals. Okay. So be super duper careful about that. Please, please, please. And again, you remember symmetry theorems are very powerful, very wonderful, but dangerous. Right? So you have to be super careful that you only apply when they actually fit, when all the conditions are satisfied. Please don't accidentally try to apply an odd symmetry theorem to a vector surface integral. It does not work. Okay. All right. So I've made a reference already to how vector line integrals and vector surface integrals seem to have a few things in common, right? Symmetry theorems, how they, when they apply, when they don't, very analogous. Geometric good fortune, this coordinate notation alternative, a lot of analogies. So I'm going to show you now a bunch more analogies between vector line integrals and vector surface integrals. I want to emphasize this is very, very surprising. Vector line integrals come from thinking about work. Vector surface integrals come from thinking about flux, right? They're totally different physics problems, totally different contexts. One of them's a surface with a normal vector. One of them's a curve with a tangent vector. They're totally different geometry. They're totally different physics contexts. But check out these analogies. Very weird. It's going to take me a minute to develop this. Bear with me. We're going to work off of a parameterization for each. Here I've drawn a version, anyway, of parameterizations. Please forgive the fact that I have them kind of written diagonally instead of, normally I would write my functions horizontally, but I just don't have enough width on the page to be able to make that work. So I angled them down a little bit, but it's still just a parametric curve, parametric surface, just like you've seen before. Okay. All right. What do we do with a parametric curve? Well, one of the first things we do is we talk about the derivative v. That's one of the important players when you're doing vector line integrals. Okay, what is the first thing that we do for a parametric surface? Well, we write down the capital N vector, and if you remind yourself, where does the capital N formula come from? It comes from derivatives, partial derivatives. But so in its way, this capital N is kind of a derivative too, sort of, if you will. Okay. Now, a bunch of equations down here of stuff we've written down previously. All of these equations that I have in this box are all old. Some form or another, we've written all of these down previously. Interestingly, though, look at how I've laid them all on the page, and the V's and the capital N's are in highly analogous places in those equations. It's a little weird, right? A little bit of an eyebrow raiser. Okay, let's move it along. What about the next thing we do? What do we do to a v vector? Well, we talk about its unit vector, namely t. What do we do with capital N? We talk about its unit vector, little n. Check out how they appear in analogous places. Right? Weirder. Okay, what about the ds scalar? ds scalar over here in the line integral context, ds means the size of that little piece of curve. Whereas over here we have a d capital S scalar. That represents the size of a piece of surface. Length versus area. Sure, geometrically different. Of course they are. But nevertheless, both representing size and both appearing exactly in the same places in these equations. It's getting pretty suspicious looking, right? Now again, I can't emphasize enough, dimensionally different, parallel versus perpendicular, work, physics origins, versus flux, fluid flows, physics origins. Totally different contexts. How come these things are laying out on the page exactly the same way? It's very weird, very unexpected. Okay. Let's see, the last part of this that I'll point out, we've talked about the dx vector, and we've talked about the ds vector. The nice features of which, again, I've already talked about how analogous these are. This is a single vector that represents both the size and orientation of this little piece of curve. This ds vector is a single vector representing both the size and orientation of this piece of surface. Very analogous in those descriptions, and again, very analogous in how they show up in these equations. So that is really surprising. Ultimately, what's going on here? Where's all this coming from? Why are these totally different constructions seemingly behaving exactly the same way? It's because they are both special cases of the same thing. Both of these are integrals of differential forms. It's just a weird, lucky break how these happen to turn out to be so similar. Both of them are differential forms. They're special cases of the same thing, and ultimately that's where all this pattern comes from. So what y'all can do with this is any understanding that you have about vector line integrals, the strength of the analogy here should allow you to translate what understanding you have from the left side into expected patterns to notice and hope for over here on the right side. And I think that's a powerful tool. Y'all have a good day. See you later. Okay.